So given that we have virtual addresses, right, the interesting thing is now every process can basically be given access to a large address space. And a common convention, again this is a convention, it is not enforced by the hardware, it is not any kind of fundamental requirement. What is usually done is that we split it up and say that we have a user space which typically goes from address 0 up to this C00, which basically corresponds to 3 GB. And the last 1 GB of RAM is reserved for kernel space. Okay. Now what exactly do we mean by that? In user space is where we have application code, application data. Let's say I have a simple program which does printf hello world. The hello world, the string is application data, the application code is basically the main and printf. There is a stack where maybe I declare a variable int x and it goes onto the stack. If I do malloc, it will go into the heap. There may be shared libraries that I am invoking and so on. Okay. Each process will have its own user space and it's in user mode access. So it's protected from others, but apart from that, this process itself can do whatever it wants. Kernel space is a bit more special. It is actually sort of shared across all processes, which means that all of them ultimately when they try accessing this will finally get mapped into the same physical frames, right. So this kernel space part of it is going to get mapped into the same set of physical frames. In order to do anything here, to access it or to run code from here, it can only be run in kernel mode, and in general even accessing it can only be done in kernel mode. Now this is again something which I have mentioned in the past. The processors themselves have protection, meaning that they have the ability to switch between user mode and kernel mode, and while in user mode they cannot even access these kind of memory locations, but while they are in kernel mode they can actually go and access this, and that will be permitted by the MMU. Okay. Which basically results in what's called privileged access, right. It's sort of a elevated level of access. This is sort of running at the kernel level. It is more or less the equivalent of the super user running code. Okay. Yeah, so various things such as the page tables, DMA buffers and so on are all stored in kernel space because those are things that directly interact with the underlying hardware. The interesting thing is now each process sees a very similar kind of view of memory. The kernel space turns out to be shared across multiple processes because anyway when you go and access anything there you have to move into kernel mode, which means the operating system is what is doing the access for all practical purposes. So a function that we have used in the past, right, to basically map peripheral registers, right, was this thing called IO remap. And what the IO remap does is it basically creates a kernel virtual mapping to a physical MMIO region, meaning that rather than memory as such, right, it is not DRAM, it is just a set of addresses which correspond to a physical memory mapped IO region. And by doing IO remap, we are basically creating a remapping in the kernel address space, right. And what it does is the MMU now needs to translate the driver's virtual address. Basically the driver ends up getting a virtual address. It still needs to be translated into a physical address through the MMU using a very similar kind of approach to what is being performed for others, right. Which means that the same kind of memory access model that we are using for general memory can also be applied to IO. Now, as we have discussed earlier, DMA is sort of a special case because there is now a new bus master which needs to be able to sort of move data around, right. And it also has some kind of special requirements. In particular, one of them is what's called contiguous memory, right. And why is contiguous memory required for DMA? Because the DMA is not going through the MMU unit, it is not going through the memory management unit, which means that it does not actually understand virtual addresses, right. So when that happens, I need to let the DMA generate direct physical addresses on the bus, and what that means is that if I am trying to do like a burst copy into a large array, I need to make sure that when I have allocated the array, it is actually one contiguous, right, meaning that connected block of memory that is present inside the physical memory of the system, right. The reason why I am making such a big deal about this is, let's go back to virtual memory over here, right? What this image is telling me is that, for example, I might have a mental model where I say that, I have an array, let me call it A, right, with let's say 20,000 entries. Okay, it's possible that the first chunk of this is getting mapped into one location out here, and some remaining addresses out here are actually getting mapped into another chunk out here, right? In other words, in physical space, they are not one after the other. But as far as the program is concerned, all it has to do is +1 +1 +1, and the addresses just sort of go automatically from one to the next. The MMU automatically, as soon as it switches from here to here, just changes the page from which, the physical frame from which it is fetching data, meaning that transparently the program doesn't know, it doesn't even sort of miss any extra cycles, provided that everything has already been brought into cache and so on, right? The latency, everything remains exactly the same. It is a very completely transparent way by which this chunk and this chunk can be made to look as though they are adjacent to each other, okay, even though there is something else, a gap in between them, right? So this is an example of what we would call, it is contiguous in the virtual space but non-contiguous in physical memory. Now that's not good for DMA, because DMA is always dealing directly with physical memory. So if I was to directly go and do a malloc, I don't have a way of controlling that the physical addresses are actually contiguous, which is why when we do DMA, what we go in is use this thing called the CMA, the contiguous memory allocator, right? Now that sounds good. The problem is, clearly there must have been a reason why we, when we ask for a malloc, the kernel might have ended up giving us two separate physical memory locations, right, and said, okay, these are next to each other. As far as your virtual addresses are concerned, they will anyway be contiguous. Now the reason why it cannot always guarantee that is because of something called fragmentation, right? Every time we do malloc free and so on, and in fact when we have multiple different processes running all at the same time, the kernel might end up allocating a chunk of memory to one process, allocating another chunk to another process, a third chunk to the first process again, at which point there's the second process memory sitting somewhere in the middle, and then maybe it frees up something else, maybe the second process frees memory, right? Now suddenly I have the third chunk sitting in the middle that has become free, but all of these different chunks for the first process are not one after the other, they are not contiguous, okay? It's a natural thing that happens all the time in running systems, and virtual memory takes care of it beautifully, right? I mean, you don't even need to know that such a thing has happened. The problem comes when we are dealing with DMA. DMA cannot deal with that, right? So what we do is we take one chunk of memory, which is typically, maybe a few tens of megabytes or so, which is reserved at boot time, right? So this CMA region is usually used specifically for DMA kind of applications and is reserved at boot time, right? And what we do is we basically say, okay, if the kernel is using this memory, it has to put only what are called movable pages in there, meaning that it can allocate this, but in such a way that if at all I need to free up that in order to get a DMA capable block, I can at least take whatever chunk of data was there, move it somewhere else, and then free up an actual contiguous chunk of memory, okay? So by doing this, we can guarantee that within the limits of the CMA space that I have, the DMA buffers can be allocated in a contiguous manner, okay? So this is one of the reserved memory regions that is usually found in embedded applications, and especially in the context of the FPGA systems that we have, there is typically also some kind of a device reserved memory where we sort of specify it in the device tree with the option saying no map, right? So we basically take a chunk of memory out there and tell the kernel, do not map anything into this. In other words, do not use it for allocating data, right? It might not have a physical range at all associated with it, but the important point is basically it says that the FPGA alone will now have access to this part of things. The kernel is not going to sort of have any virtual address getting mapped into this range. So the only way to access it would then be through physical addresses directly, right. So this can be done even using the device tree, right, and is actually, that makes it quite flexible. What we can do, for example, is we can just say that there is a chunk of memory, right, that is required for the contiguous memory allocator. We can even specify things like whether it's reusable, what are the options that it has, and so on, and we can say basically what is the driver, the CMA driver that's going to be used in order to actually access this memory and allocate it for various things, right. So all of this basically gives us flexibility and allows us to make sure that when we need to perform DMA, we can get chunks of addresses that are physically contiguous. So yeah, let's skip this. So in practice, the way that CMA gets used, of course, is, we already briefly mentioned this. We use a specific function call, right, not just the kmalloc or malloc, but it has to be something which is a DMA alloc, which knows that we are looking for memory from the coherent pool, or rather from the CMA pool, okay. And usually what happens is that when the allocation is large, if the allocation that you are looking for is very small, it's almost certainly not fragmented. So it doesn't really matter, you don't need to worry too much about whether it's contiguous memory, right. All that happens is that this function sort of takes care of it, whether you are talking about a large allocation or a small allocation, and make sure that you get a contiguous block of memory, right. And it basically sets up these pools and manages them internally. So all of this is handled by the kernel. Remember that one of the jobs of the kernel is to handle memory management, right, giving memory to processes that require it and taking it back when they free the memory and then putting it back into a pool that can then be shared among others. Now there is one more aspect of the way DMA works that needs to be addressed over here. The normal DMA that I have talked about so far, right, the way that it works is, remember I told you that DMA doesn't go through the memory management unit and therefore it deals directly with physical addresses, right. Now the problem here is the DMA device itself is an FPGA peripheral, it's sort of some IP core that's running as logic on the FPGA, and I could potentially have something which tries to set up a DMA in a way that it is trying to access either kernel code or some other memory which it should not. The worst case is that it actually goes in and tries to modify kernel code, right. And because of the fact that DMA devices can access physical addresses, right, this is dangerous. It actually is hard to prevent. So in practice, what ends up happening is, even though I said that DMA devices go through direct physical addresses, we actually have a separate memory management unit in many SOCs. This is not mandatory, but many SOCs tend to have a separate memory management unit which is purely for IOMMU, or so purely for IO, right. It's called the IOMMU, IO memory management unit. What this does is it allows you to bring protection into the picture, meaning that the DMA device provides an IO virtual address, it tries to access a particular location. The first thing the IOMMU does is check after translation, is this a physical address that the DMA is allowed to access? If it is, it permits it. If not, it basically just faults, and either crashes or basically says that cannot access this particular location in memory, right. So DMA devices, in other words, once the IOMMU is present, they will not use direct physical addresses, they use something else that is specifically called DMA virtual addresses or IO virtual addresses, right. Remember that these are not the same virtual addresses as used in a process, because the virtual addresses are process specific, whereas DMA is at the level of a driver. It's transferring data from one set of locations to another, right. So these are addresses which are once again specific to the DMA module, right, and this IOMMU does the translation of the IO virtual address to a physical address, and it handles this only for IO related issues, mostly when the request is coming from the DMA, okay. and the kernel can now take care of mapping only valid buffers, meaning that it basically can configure the IOMMU to say only these regions are valid DMA buffers. If the DMA is trying to access anything out of that range, fault. Okay. So once again, it allows you to isolate device access. It can also catch bugs in DMA if it's trying to access things it shouldn't be, right? And the interesting thing, especially nowadays, is that there is extensive use of virtualization. In fact, pretty much any time that you are using something cloud related, you have probably come across the notion of what is a virtual machine. Some of you have probably also run virtual machines on your own laptop or desktop, right? And what happens there is you have a host OS, which is actually the one that you are interacting with, but there's also a guest OS, which is the one running inside the VM. If the guest OS tries to do DMA, it can still succeed provided that it is, this kind of protection with IOMMU and so on is applied properly. So once again, the IOMMU is also something that can be specified in the device tree, and what we can do with the example that we use, the FIR filter case, right? We could probably, because in the FIR filter what we used was the DMA streaming approach, where we basically said that I can stream data into the filter. What I would need to specify is that the filter would basically need to use the IOMMU that is specified out here. Okay. So all this can be specified. I mean, these are not, in some cases they may not be required. It depends on how the driver is written, how the entire system is set up, but these are sort of recommended approaches which allow you to build drivers in such a way that they do not sort of cause system instability by trying to access things that they should not be doing.